Now we're going to see a last parametric method that uses no latent variables, which is named fully visible belief networks. As the name indicates, this method is based on neural networks. It is really difficult to model a distribution in high dimension. If the joint distribution admits a density, modeling the joint distribution is equivalent to finding the density, that is, a function from Rd to R in dimension d. Some methods circumvent this problem by assuming that the input variables are independent, conditional on the output variable. This is the case of the naive Bayes model. In practice, assuming the independence, even if it is conditioned on the output variable, is too restrictive. The method of fully visible belief networks tries to address the problem of modeling distribution in high dimensions with more flexibility than the naive Bayes model. The starting point of this method is to rewrite the density P of the joint distribution as a product of conditional distribution P of xj given x1 until xj-1. This decomposition is very generic. Regardless of the distribution, you can always use this decomposition. However, the precise decomposition depends on the order of the variables, since we first consider the distribution of x1, then the distribution of x2 given x1, and so on. Here, you see a scheme of the neural network we are going to use. The input variables are depicted at the bottom of the network. Here, the input space is of dimension 4. Then you have a hidden layer composed of units h2, h3, h4, and an output layer composed of units g1, g2, g3, g4. These last units are the parameters of univariate distributions that appear in the decomposition above. For example, g1 corresponds to the parameter of the univariate distribution of x1. Similarly, g2 corresponds to the parameter of the distribution of x2 given x1. Indeed, you see that the value of g2 depends on x1 through the hidden unit h2. If you are interested by the exact equations used to compute the hidden units and the parameters in the output layer, you can take a look at the paper at the bottom. Most of the connections are linear or use the hyperbolic tangent function. To implement this method, you need to choose parametric forms for the univariate conditional densities. Once they are chosen, the problem amounts to estimating coefficients for all univariate distributions. To do so, you can use the parameters of the network and the form of the densities to compute the log likelihood. Indeed, this network takes x as input and outputs the estimated log likelihood parameterized via the parameters of the univariate densities. The network can then be trained in order to maximize the likelihood. The original idea of fully visible belief network comes from the paper at the top that introduces a method called logistic autoregressive Bayesian network. In this paper, the network was only designed for binary discrete random variables, contrary to the previous one, which was designed for both continuous and discrete variables. There was no hidden layer, and the output function was a logistic function. All in all, the corresponding model can be written as this equation. The main difference between the first model and this one is that here you have no hidden layers. You have also two more ingredients in the first paper. The first one is related to the graphical models. The input and hidden layers are organized into groups with two specificities. First, xd is not used as input because given the ordering we have chosen, xd only appears in the univariate distribution of xd given the other variables. So the value of xd is not used as input. Of course, this variable is still used to compute the log likelihood. Besides, g1 is independent of all input variables. Indeed, here we want to estimate the parameters g1 associated with the distribution of x1, which is independent of all other variables. Another much more important ingredient is the way to choose connections in this network. Indeed, not all neurons are connected to the other ones. Some connections are removed in the diagram I have shown you 2 slides before. In order to choose the connections that can be removed, a Kolmogorov-Smirnov test is performed to assess the link between 2 variables x, j, and xl. This test is based on the joint and univariate cumulative distribution functions. The pairs of variables are then ranked according to this statistic, and only the pairs whose statistic is above a specified threshold are kept. This means that for the pairs that show a strong connection, the groups are connected in the network, both between the input and hidden layer and between the hidden and output layer. By using this method, you may drastically reduce the number of connections in the network, which also helps the optimization procedure. Here we have seen a parametric technique which uses neural networks. However, in this method, we have not access to the parameters of the distributions because they are estimated via neural network and depend on some values of the input variables.